Okay, folks, hope everybody's doing well. We are going to jump into module number 4. So again, just to show you where we're at here, we're going to be talking about mathematics today, a little introduction for folks and just refreshing some C++ structure stuff. And again, today is a holiday, so you're not meeting me now, but watching me, and then you'll rejoin next week for our next lecture, where we'll have the regular pre-recorded lecture and live sessions. Hopefully you're having a good holiday. And you will have a lab 4 that is also pushed to your repository, which I will talk about now, because just to get that out of the way. So let's go ahead and look at your lab 4, which is going to be on math. It's a 3-part lab. And spending a bit of time on it and thinking about things that we needed to review for this class. And so there's 3 parts. So part 1, which is primarily reading and supplemental videos to get folks up to speed on C++. So please read through this. I took some time to write some stuff that's relevant for the lab later, as well as just topics where I saw people were struggling with in the course. So the first part's just about building your project, explaining a little bit about what's going on here. The second part about memory management, which is always going to be a topic that keeps coming up. A little refresh on smart pointers, because we had lots of questions about that. There's a brilliant, about 11-minute video here, also talking about the different types of smart pointers that can save you hours and hours of time if you watch this and consider using them during this course. And then just some other general C++ topics that we haven't spent a lot of time on, but are worth knowing about, because you're going to see them a lot in today's library code, which I'll get to in a moment. So const, inline, and templates are worth knowing about, okay? So that's part 1. Part 2 is where you're actually going to be doing the work. You're going to be building a library called tinymath.hpp. So let me show you what that looks like. That's in the include directory, tinymath.hpp here. And you're going to be just using this library and implementing some of these functions here. Okay, so different mathematical operations. So there's plenty of resources if you need to read up on them. But most of them are relatively simple. Things like multiplication, vectors, and so on. So we're going to talk about some of these operations today during the lecture portion. All right. So the rest of part 2, otherwise, once you've implemented your library here, again, that's where we just were, a header-only library, you're going to have to test it out. So test the tinymath library. So what's new here is you're going to have another tests directory, so test.cpp, where you'll write a few unit tests that make use of your tinymath.hpp. And you'll implement these as follows. So you'll see unit test 1 here, creating 2 vectors, adding them together, checking that the result is what you think it should be, and then returning true. Otherwise, returning false, okay? So this will run the 12 unit tests, or however many functions you write. You can write as many as you like, and give you a report. And all 12 of your tests should pass. You're welcome to add more if you like, but we'd like to at least see 12 to know that your unit test, or your math library rather, is working and is being tested, okay? So that's it for part 2. So again, you have the test directory where you can test your code and write those unit tests, and then the actual math library, okay? A few other resources, again, on any of those math operations are available beyond the lecture, which we will talk about today. And then part 3 is totally optional. That means you don't have to complete it. But if you'd like, you can look at speeding up your math library using AVX instructions, which I've included a bunch of samples here, a little tutorial in 5 lessons. So you're welcome to take a look at that. Now, I will warn you, for folks who have used AVX, is not all of your operations will benefit from them. But it might be useful to take a look at some of your math operations and implement them in parallel. Which again, you don't have to, but we're going to talk about it just a little bit today because it's worth knowing as a game engine programmer. Okay, so that's lab 4, quite a bit of parts to it, but part 2 is really where the work is. So that's where your deliverables are, but part 1 is a great supplement. Okay. The last thing I'll note is that if you actually, when you do compile this, you will notice that there is some, of our sort of infrastructure for our graphics programs, and it's just demonstrating how to actually use tiny math here. Okay, so it's not going to really do anything or anything's going to show up. We're really just looking at your actual unit tests to make sure that this library is working. Okay, so that's it for the lab portion. That'll be pushed out to your repos by the time you're seeing this video. If not, let me know and we'll take care of it. But let's go ahead and dive into module number 4, Mathematics Library for Game Programmers. Okay. So just a little fun warm-up. This was a few days ago. So since the last time we met, Jonathan Blow, who's a pretty popular game programmer, famous for the game Braid, which let me put that in here, Braid game. He's recruiting game engine programmers. So little selfish promotion here on my Twitter here. But I was reading this here. Really interesting Twitter feed that he's got here. And, you know, he tweets about a lot of programming stuff, but he's actually hiring some game programmers here. So that's kind of cool to check out. So anyway, kind of fun to see what's going on in the world there, and that, yes, game engine programmers are, you know, that is a official role that you can get. So definitely worth, you know, seeing or seeking out some of these rules just to see what experience they're looking for, to get an idea of maybe things that you want to focus on in this course or otherwise, just to see what a position might be like if you're really enjoying this course and want to be a game engine programmer full-time. Okay, so last time we talked, before we move along, we talked a lot about engine support systems. So, you know, an overview of just a lot of different topics and a way to sort of bend your mind a little bit for how we think about, as game programmers, some of the optimizations that we might want to take, some different strategies we have and tools that we have as C++ programmers to make our programs run fast, but overall just give us, you know, control over our system. So we talked about the initialization shutdown pattern, how we sort of can explicitly do that for various systems. We talked a lot about performance and memory and how caching is going to be important. So we're going to talk about being sort of more data-driven in our engines, but also sort of data-oriented programming is going to sort of be our style, where we care about the data and thinking about how it's processed. Okay, so things like caching, again, will be important. And memory allocation, of course, was the other big topic there. And just knowing that we can have different memory allocation strategies for different components that we have in our games. So we talked about stacks, double stacks, pool allocators, just brief sort of introductions. We are going to build a little sort of memory framework, I guess, or memory, I don't know if I want to call it a full memory allocator yet, but a way for us to manage our memory and see at least what's going on inside our systems for, you know, debugging purposes in games, okay? Then we talked a little bit, just a really super quick overview of the standard template library, this asset pipeline, which I always like to point out is kind of, you know, interesting to think about as a game engine programmer, because, you know, you're also working with integrating things like, you know, tools that artists use and having to work with their pipeline. So we do have to think about how content gets into our games at the end of the day. We talked about some other things like asynchronous I/O, some different sort of game design / game hacks that are, you know, things that allow us to squeeze more in our games. You know, some folks made some references to sort of twisting hallways and climbing, you know, big ladders and stuff. Why are those things in games? Well, it's because usually behind the scenes, asynchronously, you're loading some resource, okay? Super brief discussion about file compression, something else that we will touch on because, again, if we're sort of memory bound in our systems and memory is so important, compressing our data and working with the compressed data might be faster, you know, as far as loading our actual data into our systems versus, and then, you know, paying a little penalty to have to decode or extract that data during runtime on our processor. So something that we think about. Okay, and then your lab 3 and the part of the end of the discussion of last lecture was about resource managers. Basically, you know, in its simplest form, I was talking with some folks about this. A resource manager, you know, if you want to just think about the most simple bare bones resource manager, it's just a map with a string as the key, maybe to some file path or resource, and then the actual data is the value. Okay, so then you can sort of look up to see if you already have loaded some resource and then share that resource in your game engine. Okay, so that's sort of the simplest it can be, but it can do other sorts of stuff like handle loading resources asynchronously, counting references to that object, being able to restart and shut down certain subsystems and so on. So we can build on top of this resource manager, but at its simplest level, or at least for the lab, it could be as simple as, using a map to manage your resources rather than loading all of your resources every time and having lots of duplicates. Just knowing that alone actually can be a big savings in your game. It's just another step from going to sort of, more professional game, just some of these little tricks here. Okay. Okay, so moving along, let's see, the course logistics here. Assignment 1 is released, so keep working on it. I've been seeing folks break out games, which is awesome. And you're completing this individually, and it is broken down into 3 parts, okay? So at this point, today it is February 15th when I'm recording this, so my expectation is you're working on at least part 1 by this point. You should have opened it up, you should be working on it. It can be a big project if you haven't started. And this is something, or lesson, I guess you want to learn sooner than later, that starting early is always better than starting late on your projects, because this course will have a big project and it's not something you can sort of throw together. So start building that habit, get started on A1 right away if you haven't already. And for those making some progress already, that's great. You're in a good position here. Okay, today, otherwise, we're going to continue looking at some core systems. We're going to look briefly, I'll just talk about a few C++ concepts. I kind of mentioned them in the lab. Those were the main things I wanted to touch on, but just on the build system at least, again, because folks have been having a little bit of trouble with that. And then, part 2 is going to be just talking about the math library that we're going to be building and some of the math operations. And then I'll briefly touch upon the AVX instructions for speeding up your math libraries. So people do take advantage of these AVX instructions or SSE instructions. You might have heard of them. But basically, the paradigm which it falls under is SIMD, which stands for you have a single instruction that can act on multiple pieces of data. So single instruction, multiple data. That's the idea here, okay? And then part of this math library, of course, is going to be working on linear algebra, okay? So we're still in sort of the core systems portion or engine support systems and going to knock out some of these other topics, I guess. So at least on unit testing, you're going to touch on the lab, the math library a little bit, and then again in the lab, just a little discussion on memory allocation, okay? Okay, so mathematics in games. Okay, again, it's our goal to learn some of this math, and there's actually lots of math in games, but it's nothing too difficult. Chances are everybody who's here has seen these topics. Maybe it's been several years since you've actually had to, use some trigonometry or even calculus. And I don't know if this is a short list or a long list, but this is really the bulk of the math that you want to have a good handle on in computer science. Not that you need to keep it in your brain all at once, but that you can look up these things and sort of understand them. So that's sort of my goal today, just to jog your memory on some of these operations. And then you can sort of implement them, or at least know why to use some of these operations as we build on them. But just looking at some of these examples, even simple things, we have position, which is stored as sort of a pair of 2 values, a tuple. Or we're going to represent it with a mathematical vector data type. Velocity, so you have a magnitude and direction. Here's just a direction here, some different vectors here, the dot product, see how that's used. But even things like, just figuring out how Mario can jump by just using a vector to model that over time is how you get these sort of smooth and, these jumps that feel good. They might not be realistic, right? Mario can't jump, 10 times his height or however much this is, but something that sort of feels good in the game here, okay? And then I'll talk about briefly some transformations and just how they're done using matrices, so those operations. in games. This is especially important in 3D programming. 2D we can get away with mostly having even just sort of vectors that have a or rather an x and a y that we're sort of manipulating with some velocity vectors. But once we get into 3D stuff, we really want to start using matrix transformations. Okay, anyway, let's start first with some C++ concepts just on project management. We had a bunch of folks working on, linking in libraries, the TTF library. Actually, the first group that I've had that was very adamant about using TTF. Other groups have found other solutions, so it's kind of interesting to see. But, basically with the TrueType font library, or any library, SDL, it's a piece of C or C++ code that someone's written over here. They've compiled it, and then you get an object file. Which could be in the form of a library like a DLL or .so or .dylib, depending on the platform you have. And then it comes in here to the linker, and the linker's job is to glue it together to the other code that we've written. Okay, so here's our lab CPP, for instance, that was compiled, our SDL graphics program.cpp, and those all get, turned into binary files here, object files, and then linked together all into one location. So that's what the linker takes care of. And then we get an executable file that we can run, okay? So just a reminder that that's the linker's job, to sort of glue everything together. And a common problem folks have is when they can't find the file here. So you have to remember to sort of point the compiler or the linker to different directories where it can find those shared libraries, okay? So let's look at how we do this in the little build.py file. That's our build system. I admit it's not the most elegant thing. It's not even the most professional thing. Okay, we'd probably use a tool like CMake and Make or Ninja or some of these other different tools to actually build our code. But this gets the job done, and it solves the problem of working on multiple platforms. So what's going on here? So I'm going to show the Mac version because we have most of our folks on Mac here. It's the same for Windows and Linux roughly. But just the little different pieces and parts again when we're compiling our code. So again, the first bit of this command string, and remember it always prints out when you run the Python 3 build.py, is your compiler. Okay, our compiler, our language standard, we're using C++ 17 for the most part in this course. And then any kind of pound defines that we want to send to our preprocessor. Okay, so in this case, we're compiling with a Mac. That's how I'm doing the conditional compilation. Okay, so let's actually see where that is in a piece of source code, like in part 2. Let's go ahead and let's look at one of the header files because that's, I believe, we're actually use it. So it's passing in that Mac symbol. So, it didn't find Linux defined or MinGW or anything, so it's going to start executing, this branch of code conditionally, okay? And say, aha, this is where SDL.h is, okay? For you Unix people and MinGW, it's located in this directory, okay? All right, so that's getting your compiler, starting to get it set up. The next part is the output portion here. So the -O here, the next part, is how we're going to name our executable. This is what our output is, okay? So then we'll run the program with ./lab or ./lab.exe or whatever for your platform, okay? And then we have the include directory. So this is, one of the trickier parts when compiling software, but the include directories say, hey, here's the file paths where all those things where you pound included or that the hashtag include all of your files, and these are places where you should look for those files, where those .h or .hpp files are. They're somewhere in this location or this location or this location or whatever. And there's certain locations your compiler will look in. If you echo out the path variable, for instance, this is on Linux, so this is how I echo out. Your compiler will default look for those files here or here. Or here, or here, anywhere between the colons. And it'll look in all of those locations and these locations that you pass in on the command line here to see, hey, can I find one of those .h or .hpp files? And if it can find it, it's satisfied, okay? And that's what it's gonna use, okay? So that's another sort of common problem. Depending on if you're using Windows, Mac, or Linux, you might have to change these files. Okay, so I've included some, for instance. header locations or even a math library that you'll have available. But that's the idea here, okay? Then the next part we have here is the actual source files that are going to be compiled. So here I just have a wildcard character, but it'll work. So all the CPP files in our source directory will get compiled, which is kind of cool. Okay, so that's what's generating all of these. If I go back here, all of these object files for each of those .cpps, and then behind the scenes, our linker is invoked and it'll glue those files together. Okay. And then the final bit here is the library. So Mac, it's a little bit different. They have a framework thing is what they call it, but same idea in Linux or Windows. If we look here, just do for Linux-L SDL-LD. For Windows here, I include some other libraries that are needed to get this up and running. But that's the idea. So here we're saying, hey, where do I look for, again, that library? Where's that .so file? Where's that .lib file or whatever that you're including here, the .dll, this location here. And then the framework, what is it actually called? So this is the object file that's been compiled and is actually going to be used here. Okay, so that's what we need to specify here, that we want to use this one. Okay, and we do that with -framework on Mac. In Linux, we do -L. That's not part of the name, but it's just telling the compiler and then thus the linker, which is brought in automatically for us, to look for SDL2, something that's named that. Okay. So oftentimes, if you can't find a library, this is, you can try this path here. And you can try the absolute file path first to see if that works, and then try to figure out how to get the relative file path to work. So again, absolute file path just means the full file path, the whole location here. And the relative one, remember, is relative to where the .lab executable is. Okay, so if it's in your bin directory or on your desktop or whatever it is, this relative file path needs to be, again, relative to where the actual executable is that you're trying to run. Okay, so I saw a few people who had that issue when getting up and running. Okay, so just some things to keep in mind when building your source code. Okay. Okay, so why am I going over this? One, just to make sure we sort of troubleshoot folks who are having difficult, but the second is, today we are building a math library. Okay. It's a series of functions that we're going to use, and potentially we would want to use this for other projects too. So we have some decision to make about how do we design this thing? Do we compile it and load it as a library, almost in the way that SDL is? Or do we implement, the interface and have an implementation and just compile it in our project? Or do I just write everything into a header file and just include that? Because that's also an option. And my question for folks, if you want to pause the video and take a moment to think about it, is what are the trade-offs of each of these, three approaches here? And if you've paused the video and taken a moment to think about it, here are some of my suggestions, or the pretend discussion that I think we're going to have, or maybe thought we were going to have, on just some of the pros or cons. And some of these are controversial. This is just some thoughts. They aren't concrete facts, but why some people make these sort of trade-offs. But if we wanted to compile it and load it as a library, that sort of makes sense. Again, especially if we're sharing it amongst multiple projects, and especially if we don't want to, distribute the code, right, with the project. Okay, so I'll actually make a note about that, especially if we don't want to share the code. Okay. Why that matters sometimes, I'll make this a little bit smaller, is if you have intellectual property. You're going to find out that's one of my motivations of why we do things in this course, because you want to be building some, intellectual property. I think so, as sort of an entrepreneur. If you have some proprietary math library that's really, really good, and you don't want to give away your trade secrets. Okay, so compiling it's a perfectly valid reason to want to do that. Now the cons are on that side of having to compile it as a library every time is that you might have to support multiple platforms. That causes some overhead. Dynamic linking can cause a sort of small performance penalty, at least at the linking stage, maybe the actual function calls as well. So That's something to think about. Okay, so you might say, oh, well, we want the top performance, so let's just implement it the old way. We'll, distribute the HPP and the .cpp and just compile it into our project. Again, if we compile directly into our code, that's potentially good for optimizations. We can see all the functions, we know exactly how it works, and so on. And the only one I could really think of, for this strategy compared to at least the next one, is it's probably going to be a little bit more to manage than if we just say, hey, let's just implement everything in the header. Okay, so that gets us to our third point. Should we just create it as a header-only library? In the Pro, there is just really simple to implement. It's easy to distribute. Everything's in just one .hpp file. You probably shouldn't do this. It makes it a little bit hard to debug. So I'll actually add that to the cons list. Harder to debug. Along with it might actually slow down some of the compilation speed. Okay, because anytime you make a change in a file or this .hpp file, then any other file that potentially includes it has to recompile. So folks typically don't like this. We're going to do it anyways because it's easy to implement. Okay, but we might think about instead, just having an interface and an implementation instead. Okay. So again, there's sort of pros and cons to this. This last style that we're going to do is really popular these days. A lot of bigger projects would argue many more reasons against it, but our projects probably aren't going to get much bigger than say 10,000 lines of code by the end of this, so we should be okay. Okay, so let's talk about building a math library. Again, sort of the key components that we're going to need. Okay, I briefly showed you what you're going to build, but here's the pieces. We probably need a vector 2D, 3D, a matrix library, 3x3 or 4x4 matrices. These are for our transformations, how we're going to move around our game objects. We need to make sure that our data structures are correct. So these things that we build and have some unit tests. So that's what we are going to do. And we probably want to make sure these data structures are easily accessible. So this means we're probably going to do a little bit of operator overloading in C++. So what does that mean? Well, let's just look at our code here. Let's look at the library, the TinyMath HPP. And for these vector operations, right, they are mathematical operations. So I probably want to be able to do times equals or plus equals operator, or some of those, operators that are just sort of nice to have here. Okay. There's or just the subtract or just the plus operator and so on. Okay. Folks generally shy away or shun this idea of operator overloading, except in the case of some of these data structures, which we're going to use. This is probably a good use case of them, right? Using plus and minus and having those available in our code. Okay. Okay, so the second thing we need to keep in mind for our math library is to make sure the math operations are fast and lightweight. Okay, so that might mean parallelization. That's the sort of optional part 3, which we'll get to the end of the lecture. And we would typically want to measure performance in some way, maybe with a tool like perf or something, any profiler, just to know how good we're doing on our performance. Okay. For now, and for our purposes, we probably just care about having a library that's correct and pretty good. And you'll have a constraint in your math library in that you can't use any loops. So we'll know it'll be pretty decently fast. And we're going to inline a lot of the functions, which you'll see what that means in the lab, which probably makes it pretty decent and pretty fast. In fact, there's some other optimizations you're going to notice where we pass things by reference a lot, which is good. So we're avoiding a lot of copies. So, we're doing a pretty decent job here. Things are inlined. So is it going to beat NVIDIA's math library? I don't know. But it's probably going to do a pretty good job. This is based off of a pretty good library, the lab that you're building today. I'll tell you that. Okay, so again, why are we going through this process? Well, I guess the zero bolt is you're going to need some math functions here in this class, but you know, first and foremost, it's better than just doing the ad hoc calculations or having a bunch of free functions. The second is, again, I like the idea of you controlling your own IP, or, you know, having some actual libraries to your name that you've built. You know, and you're going to have exactly, since you control everything, exactly what you need for your game. You can always implement or build on top of it. And then, you know, thirdly, this is a good exercise in just building libraries, and math libraries are also nice to test. So it gets a little bit of practice testing, you know, how they work, and, you know, you're able to sort of have some confidence knowing what you built here works, as opposed to using somebody else's, because you're going to actually unit test it. Okay. Okay, so let's go ahead and dive into some review here, some concepts in game math, just so you know what's going on here. Okay, so typically, again, when we talk about values in games, we call them maybe scalars. We might refer to them by their points, but this is the simplest sort of value you have, just some, you know, floating point value here, or an integer or whatever. Typically in games, it's going to be enough for us to just use floats. So again, if I hop back here to our library and I search for floats, you're going to notice I'm just using floats for the precision. And some folks might say, well, why not doubles? Well, doubles are more expensive. Why not integers? Well, integers don't give us, you know, decimal precision. So floats are usually fast enough. You know, floating point computations are a little bit more expensive, but they're not as slow as doubles, and they're you know, precise enough for most of our needs in games. Okay. Okay, so the next idea is, you know, points that we're going to be working with fall in a space. So the one that we're most familiar with is the Cartesian coordinate space, or likely that we're most familiar with. And that means you have a point that falls in some 2D or 3D space. So just a coordinate, you know, 2D coordinate to 2, the x and y axes, or a 3D coordinate 2, 3, 5, and an x, y, z axes here. Okay, so here's an idea. Here's a little demo if you need some practice on where different you know, coordinates are in the 2D coordination Cartesian coordinate space. Okay, now as I mentioned, you can have different spaces. So you can also have a point in cylindrical coordinates. Okay, so you know, another example here, but sometimes it's nice to be able to model putting points around a cylinder. Okay, often this can be useful for things like your camera in your game if you want to sort of move around in a circle, or geometrically if you're just sort of modeling objects, you know, cylinders. You'll need to likely put them in this sort of space here. Okay, and then we also have spherical coordinate spaces, again, useful for things, again, like cameras, where you want to be able to rotate about a point in a circle here, or excuse me, a sphere. That can be also useful. So there's a conversion that you can do to go from Cartesian XYZ to spherical coordinates. Okay, and here is the process. Okay. Something that also comes up, again, folks who have taken graphics, this will be pretty familiar. Folks who've taken maybe an electrical engineering or a mechanical engineering course, maybe you learned about the left hand or right hand rule. And this is just sort of an aside, but if you sort of hold your hand up like this, your thumb is the sort of up vector, so where is up in the world. Your index finger is where is going forward, and your middle finger is what's called the right vector, so where is sort of the z-axis, I guess, pointing. Okay, so if you point with your hand, your thumb is your I guess it depends how you orient it, but usually your thumb is your x. Well, I guess it can depend here, but but usually I'll put myself here. I'm holding it like this, so my thumb is pointing to the right here, and that's my x-axis. My y-axis, which is my index finger here, is the y, and then my z, which is my middle finger, is the positive z direction. Okay, so that's your sort of right-hand rule here. So this diagram isn't as good, but anyway, that's the idea here. Okay. Okay, so let's get to our pieces and components for our math library. Vectors. We get a quantity that has a magnitude and a direction in some n-dimensional space. Again, it's visualized as having a tail and a head. So where the arrow is, that's sort of showing you your direction, where it's pointing outward here. Okay. So that's the idea with a vector. And again, it's just going to store. So this vector would store 3, 3, and then we're sort of assuming that it's coming from the origin here when we have this vector here. Okay. Now you might have used some data structure. This is probably true for most of the game dev students who've taken game programming, or if you've used Unity 3D, where you have something like a vector3 data structure, and sometimes it represents a point in the context of when you're just using this data structure because it has an x, y, and z. And that's what's known as a position vector. And that just means it's 3 values, a triple of scalars, or a 3 tuple. And that is different from the mathematical form of vector, which is something that has magnitude and a direction. Okay, so you can have this sort of positional vector, but if you have something with a magnitude and direction, that's a mathematical vector. Okay. So anyway, here's a sample of a vector 3D that you'll start out with, something that looks like this. And it's going to support a series of operations for things like addition, multiplication, and so on. Okay, so it just stores x, y, and z here. Okay, here's your default constructor. Here's another constructor where you can initialize it with an x, y, and z value. And then you have other operators which are going to overload, so things like the brackets, so that you can just reference an index here and get the x, y, and z here. Okay. Now this is a little bit of a weird thing here. Let me quiz your systems knowledge. Now not everybody's taken systems, I guess, but here I'm just getting the address of x here. Okay, parentheses, and then I have brackets I, and I is an offset. It's saying, hey, how many bytes in memory should I offset here from x? Okay, so if I put in 0 here, this actually just gives me this x back. If I put in 1 here, well, the next thing in memory here that's laid out is actually this y here. Okay, and then if I put in a 2 here, the next thing in memory that's referenced is actually the z here. Okay, so that's a little bit of a hack here of how this operator's being used. It's a simple way to implement things, but we're just offsetting into memory. And these 3 values will happen to be laid out in memory, one after the other. Okay, so occasionally you might see something like this. Okay. Operations like multiplication is something we can do with vectors. We can just multiply them by a scalar, which takes each of the individual components and multiplies them by that scalar value. Okay. So that's effectively lengthening your vector when you multiply by 2. You're taking one of the vectors, finding the arrow here, or the head of the arrow, and then just adding the vector on top of it. Okay, and that gives you 2 times the original vector. Okay. Okay, again, C++ things that you're going to see. So in your library, when you see this multiplication here, where you're multiplying by a scalar, you will see that it returns a reference here. Okay, so there's a reference type here. And this actually avoids a copy. So let's actually, again, look at it in the code to have some context here. So we're in vector 3D. Actually, you're going to see this all over the place. Where you're returning the vector here. Let's find that exact one that we're doing, the multiplication. Here we are. So we're actually returning, the reference to our actual. So this is the object that we're referring to, and we're dereferencing it. So it says, hey, give me this actual object back. And then we're just returning a reference back to that actual object. Okay, So if I just return this object, this is a pointer, so this would give us the address. We're dereferencing it to say, hey, give me an actual 3D vector. So that's why we're returning with the ampersand after. This means return an actual reference, okay? So that might be a little bit something new for the return types that you haven't seen in C++, for instance. Okay, and by doing that, we avoid a copy, okay? Instead of just returning a vector 3D, we would have to make a copy of that data structure, invoke the copy constructor, and so on. But we just say, hey, return the actual vector 3D here. Okay. Other operations, sometimes you might see on vectors, multiplication by non-uniform scalar. That just means we can have scalars, s of x, s of y, s of z that have different values, and that just is a component-wise multiplication. Okay. Addition and subtraction of vectors. Again, this would work sort of as expected, but just each component at a time. Subtracting one from the other or adding one to the other, whichever operation you're doing, for each of the respective components. Okay, so again, where would you want to use this? For example, Mario jumping. So whenever you jumped in Super Mario, the first jump, you would take Mario's x and y position and then add a velocity of 1, 3 to the first jump. So whatever direction Mario is running, plus 1. 3 up on the y-axis, and then if you hit jump again to hit that double jump, you add a velocity of 1 and 2, and then you get this nice sort of arcing jump here. Okay, and then you slowly, apply gravity and then reduce, sort of apply some drag on Mario so that he slows down from moving forward, and that's kind of cool. So that's again how you'd sort of use addition and subtraction of vectors. Okay, something to keep in mind when you're working with points in Cartesian coordinates, we can add directions just like we did in the Mario case here, where we're adding sort of velocities here. And get a new direction. We can subtract directions and get the direction as well. We can add a point plus a direction, and then we get a new point back. You can imagine it sort of just moving around. We can subtract 2 points together and get a direction, but if we have 2 points that we're working with and add them, that doesn't really make sense. So if I have a point at 1, 1 and another point at 2, 2, and I add them, 2 points together doesn't really make sense. So we can't really do it. So just something to keep in mind if you're working with points or directions, even if you're using the same, vector 3D, just something to sort of keep in mind what you're doing with those operations. Okay. So sometimes we want to know the magnitude or the length of a vector. Okay, so how do we do that? So we take the square root of all the squares of each of the components, and we get the magnitude. Okay, the vector. Okay, so that's sort of the length here. And again, new C++ thing. So how to compute the magnitude? You'll see the inline function, which I talked about a little bit in part 1 of the lab. What this inline's doing. Okay. So magnitude of the vector sort of usage. If you have this ship that's moving around and want to sort of compute its magnitude. So if it's moving, in this direction. If it's moving really fast, right? This is the direction as 4, 3. Maybe we want to sort of shake the screen because it's moving really fast. So we compute the magnitude of this vector. So it's moving at this sort of velocity 4, 3. So that's a big, magnitude that we compute 5 and shake the screen, 5 pixels. Versus if it was moving really slow, 1, 2, sort of in this velocity here, it'd be moving much slower, and then just don't shake the screen as much if it's, heading this direction. Okay, not as fast. Okay, so there's all sorts of kind of use cases like that you can think about for again how to use these little math functions. Okay, so oftentimes though when we're working with vectors, we want to normalize them. So in order to do that, we often want to work with unit vectors. Okay, so sort of this idea of setting a vector's magnitude to 1 here. Okay, so this function here is an example of what you'll do, which is normalizing the vector. It's not generating a new vector, it's just say sort of normalizing it so it's between value of 0 and 1. So you won't see values like 4 and 3, but everything's within the same range of 0 and 1. Okay, why do you want to normalize everything? One, it just kind of makes things a little bit easier because often you have to sort of clamp your values between 0 and 1 anyway. But it can be helpful to, if you have a bunch of unit vectors and you're sort of multiplying through the results, so you have some projectile, if you watch this sort of banana, it's firing in a particular direction here. Okay, so you maybe normalize that, whatever that direction is, some value. And then as it bounces, you would, normalize it maybe again just to figure out the direction of where it's pointing, rather than 700, units or something, you would just use between 0 and 1 and then multiply that by some scalar to figure out, how fast is this thing moving. Okay, it just makes life a little bit easier to work with. Angry Birds is probably using the same thing, when you sort of drag the bird on the slingshot and fire it. The actual direction or that the bird's moving, you would want to sort of normalize that value. Okay. Now, normal vector, what you're actually getting, whether it's, if it's, usually we talk about these in 3D, is something that's perpendicular to a surface. Okay, so this is used a lot in things like lighting calculations. We'll talk a little bit about 3D in this course. Later, we'll sort of talk more about sort of rendering engines and stuff. But if we have a vector that's perpendicular to a surface, so this point here, that means it's sort of sticking up like the needle on a hedgehog or a porcupine, if you want to think about it that way. Then that tells us this direction. And then if I have a light source, I can sort of compute the angle between where the light's coming from and then this vector. And then that tells me how much to light up this particular component of this sphere. Okay. And to figure out the angle between two vectors, we do this all the time. We use something called the dot product. Okay, so if I take the dot product of two vectors and I get a value of 1, then I know those two objects, which are represented by vectors, are moving in the same direction. They're collinear. If I get a product of 0, that means they're perpendicular to each other. Okay, so how do I compute the dot product? Well, here's my vector A, vector B. Take the dot product of them, and I do a component-wise multiplication of each of their components, and then I get some scalar back. Okay, and then I can equivalently, take the magnitudes of the vectors A and B and multiply by some cosine of theta, and that's also how I can compute the dot product. So this is also equivalent. Okay, and if I want to get the actual angle in sort of degrees, I can take the dot product and divide by the magnitudes, or just move these things, divide the equation by the magnitudes of A and B, and get that angle back if the angle is actually important. Okay. So computing the dot product is commutative, so you can switch the order of these operations. Dot product is also distributive with addition, right? So I can distribute this if I'm just adding these components here. Okay. Some use cases where you might want to use the dot product, and it's useful just to see where you use these tools. Again, computing the angle between two vectors. So if this is your, Yoshi, this character on a cart here, and you're going to hit this boost thruster here, well, you can figure out what angle you have between these vectors to figure out, did I hit it right on? If I hit it right on, maybe I boost the character faster. But if I hit it at, less of an angle, maybe only boost a little bit. Or for less as long. So that's sort of a practical use case here. Other practical use cases might be, if you have a character sneaking around in a game, you would want to, see what the dot product is. If they're looking in the same direction, then, the enemy probably doesn't see you if they're in front of you. Or if you're perpendicular, maybe the enemy can see you. You're in their line of sight, okay? If the dot product's greater than 0, again, the angle is less than 90. If it's less than 0, that means you're moving in the opposite direction. So maybe, again, the enemy or bad guy can't see you, okay? Again, it's useful for lighting computations, like we talk about all the time in graphics. So those are just some uses of dot product. Okay. Cross product is the other operation that we frequently do, and the cross product of two vectors produces another vector perpendicular to both vectors. So it's sort of normal to both those vectors. Again, this is used a lot in graphics when you need another to compute another vector that's perpendicular. Okay. It's not commutative, but it is anti-commutative. Okay, so I can take the negation of b and multiply it by a, and that's the same as a crossed with b. Okay. Cross product in 2D applications I'm trying to think of, not as frequently used. I mean, occasionally you might want, if you have two characters sort of, I mean, here's an application, and it's worth drawing some of these things. Again, just to get the idea of what's going on, so bear with me. Let me just get my drawing set up here. And I'm going to move this here just so you can see me. But if I have some character here and they're sort of moving in this direction, and I have another character here, and let's say they're moving in this direction here. I'm going to give myself sort of a hard one here. So here's character 2, here's character 1. And let's say they collide and there's a explosion here. And you want to generate a sort of realistic effect here. You might compute a sort of a third vector here that's perpendicular to both of these, and have some sort of effect in that direction. And then you might also take this vector here and take it with your character and compute another vector that's perpendicular to both of those, and then repeat this process and sort of get this sort of nice natural feeling, collision effect, I guess, in your game. Okay, so that's how you might use it in 2D to create some sort of interesting effects here. Okay. Okay. So those are some of the basic vector operations. And now let me take you to talk a little bit about matrices. Okay. And again, some folks have seen this in your linear algebra class, or for the undergrads, 2810, you've likely seen this, maybe in the game programming. And for grads, you've probably seen these at some point. And then, of course, you've seen this in graphics. But a matrix, or the idea of a matrix, is it's a rectangular array of n by n scalars. So here's an example. This is a 3 by 3 matrix. In 3D games, we like 4 by 4 matrices. And they make transformations work nicely for us. Okay. We probably won't use them as much for 2D games, but there are some use cases where we'll do some transformations, or could. But here's what your data structure looks like. Okay, so it's we're going to do a 3D matrix here, or 3 by 3. Here's sort of setting up the constructor, and you can also instantiate it with 3 vectors. And these are sort of our operations for us to implement. Okay, the main operation that we do with matrices is matrix multiplication, which is the dot product of the rows by the columns, which gives us a new row and column. So this is row 1. So I take 1 times 7, 2 times 9, 3 times 11. And then I, because this is row 1, column 1, this goes in our new matrix at row 1, column 1. So it fits into here. Okay, here's sort of the animated version of that if you want to see each step at a time, how to do this. And for your matrix multiplication, you're going to do this by hand. It's sort of the one, a little bit tedious. You don't want to use any loops, but you'll compute all these dot products for all 9 of the values, okay, and in your matrix. Okay, now the key thing to remember with matrices is that order matters. So you can sort of think about matrix multiplication as concatenation. So A times B is not the same as B times A, because if you imagine these just as strings, AB is not the same as BA, okay? So multiplications are chained together. And that's really the key, because they're chained together, of what makes them actually really fast in graphics, how we can sort of compose them to represent translation, scaling, and rotation, all in sort of one matrix. Okay. Okay, so that's sort of your crash course in math review for some. So I realize we've got a wide range of folks in this class, but these are sort of the main math components that we'll need to get through. And we're going to start by just implementing these particular operations here, okay? Then you'll be able to add onto your math library as you use some of these operations, okay? So for your lab, again, you're going to practice some C++ in your math. You're going to implement the vector3 and the matrix 3D library. Optionally, you'll explore the AVX instructions. So before you get started on that, just a few words on what the optional part is about with SIMD instructions, okay? Again, this part's optional, but just for your sort of enrichment, we're talking about parallelism, instruction level parallelism. Because your modern CPUs have multiple function units for doing work. So this is sort of a simplified CPU, but what I want to show you here is you have three ALUs here that are doing arithmetic here, okay? And that means you can do 3 add operations at once. And you know, these are your sort of functional units or your execution units that can actually execute work. So you can do 3 different add operations. Okay. And what this architecture is showing here, you know, this simplified, just focus on this part since there's 3 arithmetic things here, is that you can do in one cycle on your CPU 3 adds, 3 multiplies, 3 subtracts roughly on each of those units here, okay? So that means you can do quite a bit of work in parallel. And there's really little effort that's needed to do that. And this technology is actually old. It goes back to like the early 90s that we've had this sort of parallelism. A lot of programmers just don't exploit it because it's a little bit extra effort and they don't want to do it. So if we look at some newer, new-ish CPUs, I guess, Haswell, like Intel's, you know, one of their i7 4th core chips, they have 4 integer and 4 floating point functional units. They have, you know, you can do multiple stores. So if you're, or loads, excuse me. So if you're just reading memory, you can do 2 at a time, 1 store. And these are the different types of operations you can do. 4 integer, 2 floating point computations, 1 floating point add, 1 floating point divide, all at once in the same cycle. Haswell is probably a little bit old, so if you're really like interested in this stuff, I taught last semester the performance engineering course, which was sort of a new experimental course. And since that picture kills me a little bit, you can look at another take on this SIMD stuff. I just want to show you what a modern CPU looks like, even newer than Haswell. This is a more accurate picture here. This is from, let me see, Coffee Lake. And if you're really reading the news, Intel is doing Rocket Lake, apparently. But this is the amount of execution units you have. So you can look at how many integers operations you can do and sort of count them up. Here's your vector ALUs, which we'll get into in a moment. So there's a lot more in a modern architecture of things that we can do in parallel, okay? This is your parallelism here. A little bit of a different diagram, but actually pretty cool to look at here. But anyway, back to ours. Here's Haswell. Same idea. So anyway, so with instruction level parallelism, hardware can execute multiple instructions at once. You know, oftentimes, again, we don't do that because we have different data dependencies. But if we look at some of our math operations, you know, when I'm doing a component by component level addition or multiplication, there's no dependency, right? Let me show you what I mean by that visually. Let's open a graph here. And again, remember, if we're doing sort of x, y, and z of vector 1, and we're multiplying that by some scalar, I'm applying this value to x, y, and z independently, right? There's no dependence between x and y here, okay? So I can do this in parallel. I should be able to multiply these 3 values all at once by this scalar, okay? And for compilers to figure that out, that's kind of difficult. But for us as humans to say, oh yeah, we're just multiplying, x, y, and z by, some scalar value, that's actually pretty easy for us to figure out, right? Some compilers are pretty good and can figure it out, but not always. So we need to know a little bit more, and this is the idea of SIMD programming, okay? So Intel released these things called the streaming SIMD extensions. That's what SSE stands for. And then now they have the advanced vector instructions, so same sort of family, AVX and AVX512. These are the instruction sets that let us have some functions so we can do things in parallel. Okay. A little fun fact, I worked on this while I was at Intel in 2016. That's what I worked on. Okay, the idea with these, again, is we have some special registers. You can think of those like variables that store a bunch of data. Let's just say you have 2 of them, and you want to store a bunch of floats in each of these registers, so these sort of special variables. And then you can actually do 8 multiplications at once here. So here's the example here. I have a register here. You can just think of it as a variable again with 1s in it. Okay, and this is setting up the single precision floats here. That's what the sort of PS stands for. I'm setting them up as just 1 in each of the sort of slots here. I've got 256 bits, so I can fit, if a float is 32 bits, then I can fit 8 of them into this register. And then same things here, where I'm just counting 1, 2, 3, 4, 5 in another register. Okay, so 8 floats per register. Then I can subtract all the 8 floats from one register in another, right? It's the same operation. I'm just doing 1 at a time here. So I'm doing these 2, and then these 2, and then these 2, and then these 2, and then these 2. And this just happens in one cycle here. Okay, I'm applying this same instruction, this subtraction, to each of the independent sets of bits here, every 32 bits. Okay, that's the single instruction sub on multiple pieces of data here. Okay. Okay, so, and then you can extract the results. You essentially get a pointer here and then offset. A float is 4 bytes. So every time you use this offset, you're just offsetting 4 bytes of your 256 here. Okay, so you can print it out. Okay, so there's a bunch of examples included again in your lab if you want to play around with this. They're worth knowing as a game engine programmer because you could end up implementing some of these from scratch. Not required if you're just saying, hey, I'm totally lost. I don't want to work with these intrinsics. No worries, but I want some folks to know about them, okay? Again, here's just the idea that you have these sort of 256-bit registers, at least with AVX2, and the idea that you can pack a bunch of integers, so 8 32-bit integers into one of these registers and perform the same operation on all of them at once. Okay. So here's the idea. The naming conventions are a little bit weird for these registers, but you'll see the data types here. Just like in C++, we have primitive data types like int, char, float, etc. With the AVX instructions, we have our primitives, which start with 2 underscores and then how many bits you're working. And then the suffix, it tells you what the data type is. So D means it's doubles, I for integers. If there's no suffix, it's a float, because most commonly we're working with floats. So that's how we type it out. So here's just 256 bits that understands how to work with floating point data. Okay. So again, in the actual instructions that you'll use, the function, so you have an underscore mm, the bit width, so usually 256, underscore the name, so this will be like add, subtract, multiply, or whatever, and underscore, and then the data type. So this will be something like PS if you're working with floats, or D if you're working with doubles, or I, or SI if you're working with signed integers, or these kind of things, okay? So here's just another example of it. You've got some of these ready to go for you in your lab if you need them, but that's it, okay? So some of the libraries that you're likely to use, the GLM library is probably one of the most popular, but they have a bunch of these instructions already set up with SIMD for us. And sometimes they can be faster, not always. I might share a use case if we have time next time we talk, or if folks have questions about a student who actually did implement these and found out that the time taken to set up some of these registers may or may not be worth it depending on what operation you're doing. So that's kind of a fun experiment that they did. And if folks are curious, I'm happy to share that. Okay. So anyway, you have a few examples here. That's sort of bonus content, but stuff worth looking at. I believe Jason Gregory in his text, the Game Engine Architecture book, does talk a little bit about these AVX instructions too, if you're following along there. Okay, so with that said, you should have your in-class activity ready. You have a nice lab that you should start, and then keep working on your assignments, and then we will resume in person very, very soon, folks. So I hope everybody otherwise is well, and we'll see you next week when we're in session.